texture like sun lays me down. With my mind she runs throughout the night.
The concept video for a method of undetermined coefficients. So this method is used when trying to solve inhomogeneous second-order differential equations. So that's going to be an equation in the form y double prime plus py prime plus qy equals some f of t. So trying to find the solution to this equation. And the way we do that is we look at the associated, so like this is, first of all, inhomogeneous equation. So we look at the associated homogeneous equation. And that's just going to be y double prime plus py prime plus qy equals 0. So we have a 0 instead of a function. And I'll put a subscript h on this y to indicate that it's a different y than our inhomogeneous equation. So this has the solution. YH of t. So our YH of t, that's just going to be C1 Y1 plus C2 Y2, where Y1 and Y2 are part of the fundamental solution set. So the solution to this equation, this inhomogeneous equation, the solution y of t is going to equal this homogeneous equation yh of t plus a particular solution yp of t. And this is going to be, this is linearly independent from YH. So this method of undetermined coefficients is just going to be about finding this particular solution. So the particular solution, what we're going to do is we have to guess what yp looks like based on what f of t is. So we'll list out possible choices for f of t, and we'll show you what the guess is for y particular, or yp. So if f of t is an exponential, so let's say e to the at, then yp, our guess is going to be some constant k times e to the same at. This also works if we're using a base other than e. If f of t is cosine omega t or sine omega t, or omega is any arbitrary constant, then our yp, our trial solution, is going to be a cosine omega t plus b sine omega t. So whether or not we have cosine or sine, we're going to have to plug in both sine and cosine. And if we have a polynomial of degree p, so that might look something like this: a t to the p power plus b to the t, bt to the p minus 1 power, all the way to some constant z. Then our trial solution is going to be a polynomial of degree p, another arbitrary polynomial of degree p. So this might look like lowercase a times t to the p plus lowercase b times t to the p minus 1, all the way to some constant gamma. These are all arbitrary constants. So for f of t, we're going to get definite values for this a, this omega, and this a, b, and c, and p. But for our trial solution, we're going to have to leave these arbitrary and plug our particular solution back into our equation and solve for the constants. So now if we have, those are the three main cases. Now if we have a product of exponential functions, trig functions, or polynomial functions, our trial solution is going to be the same kind of product, or going to be a product of arbitrary exponential trig or polynomial. And we're just going to multiply these arbitrary trial solutions into the product. And same goes for, we have a sum of the same thing. Our trial solution is also going to be a sum of this. This will make more sense once you see some examples. So that's an overview of the method. Next thing you do is plug yp into an inhomogeneous equation, and then solve for constants. That's it. Then you have your solution, y of t equals yh plus yp. One more note, if your yp, so if yp ends up being linearly independent, use Li as an abbreviation, linearly independent, or dependent, sorry, not being linearly independent from yh after using the trial solution, multiply yp by t and plug it back into your inhomogeneous equation to find constants. So that's just one extra note, and that'll make more sense once you see some examples.